Okay, hi TFA, how are you? This is homework for Monday evening for Tuesday. And again, I like to try and make sure I keep this light, okay? So really tonight is just doing a little bit more work with imaginary numbers, okay? And just mostly it's going to be some vocabulary, maybe some algebra, but mostly vocabulary, okay? We'll also be talking about simplifying rationals as well, since it kind of goes handily here. So if we look at this number that I wrote here, 3 plus 2i, okay, this is called an imaginary number, or sorry, this is called a complex number. And a complex number is of the form a plus bi. That's just the kind of standard form of a complex number. And what you see here is that a complex number is a sum. It's a sum of a real number and an imaginary number, because an imaginary number is just the number like 2i or I or 17i. So the sum of a real number and an imaginary number is what we call a complex number. And what's really cool about this is that if you think about it, the world of real numbers and imaginary numbers, they do not exist. They do not overlap, right? Real numbers exist here. Imaginary numbers are all over here, right? There's no overlap in these two sets of numbers. You know, imaginary numbers are numbers that involve the square root of some negative. Real numbers don't. But the set that includes both real numbers and imaginary numbers is the larger set, complex numbers. And the reason why complex numbers include both is because if you look at this form of a complex number, a plus bi, right? If a equals 0, then you're just left with an imaginary number, bi. And if b equals 0, you're just left with a real number, the a part. So here, for example, you know, if we look at this, a plus bi, the a here is 3, the bi part is 2a. Now again, this is the general form of a complex number, a plus bi, but don't be so literal. It doesn't mean it's always going to be plus. So for example, negative 11 minus 3i is also a complex number. Here, the a would be negative 11, and the bi part here would be negative 3i, because you could write this as negative 11 plus negative 3i if you really wanted to flesh it out and have very clearly the a plus the bi part. Okay, so now you know what a complex number is. A complex number is a sum of a real and an imaginary number. Okay, we're going to take a little sidestep here, and this should be very comfortable for you, a sidestep into simplifying radicals, okay, simplifying radical expressions. And this should be a walk through Math 2, for sure, if not mostly Math 1. So let's just deal with something like this. You had things like this, right? And up until this point in our math work, I just said, oh, just leave it as, square root of 27, or leave it as square root of 75. I'll review simplifying radicals in a minute. Well, the time has come. Let's review this now. So when you're simplifying a square root, right, and these are just square roots right now, what's helpful is for you to remember those perfect square numbers. Perfect square numbers are like 1, 4, 9, 16, 25, 36, etc. These are perfect square numbers because they have exactly a perfect square root. Okay, so if I look at radical 75, or the square root of 75, it's helpful to ask yourself, is the radicand, and just some vocabulary, the radicand is that which is under the radical, okay? Is the radicand divisible by a perfect square number? And here you can see, hopefully fairly clearly, the answer is yes. Square root of 75 is definitely divisible by 25, and I can rewrite this as the square root of 3 times the square root of 25, which then becomes the 5 times root 3. Okay, square root of 32. Now here's what's interesting. Maybe you don't see the biggest perfect square that divides into radical 32. Maybe you just see that 32 is divisible by 4. There's nothing wrong with that, right? Many people don't necessarily think of the largest perfect square number. But if you rewrite square root of 32 as root 8 times root 4, you'll see, oh, well, root 4 is just 2, and now I'm down to 2 root 8. And you know that your radical is fully simplified if the radicand is no longer divisible by a perfect square number. So here you see that 8 is still divisible by 4. So you then would rewrite the square root of 8 as this, right? 2 times root 4 times root 2. And then root 4 here is 2. At the end of the day, we get 4 root 2. And this would be the simplest radical expression, okay? So it helps to ask yourself, is the radicand divisible by a perfect square number? And if so, what is the largest perfect square number? All right, so square root of 27 would just become 3 root 3. Now, I will say this, a lot of people, once they feel comfortable, skip this step, like the step where they write both the square roots out, right? A lot of people will just go to that step here and just will write this as root 3 times 5, root 8 times 2, or 3 times root 3. And I have no problem with you doing that, but make sure that you're really comfortable and swift before you go there. All right, so that is simplifying radicals, everybody. Simplifying radicals just ensures that your radicand is no longer divisible by a perfect square. Now I'm going to loop negative radicands into here. So let's take a look at square root of negative 9. Okay, before the introduction of imaginary numbers, we would have left square root of negative 9 as it is, and we may have even written this doesn't exist. But now I can do this, right? I can write this as square root of 9 times the square root of negative 1. And in fact, we know that whenever we have a square root of a negative number, the root negative 1 can always come out. And we know that root negative 1 just equals I. And radical 9 is 3. So from now until the end of time for you all, you will no longer write root negative 9 as just root negative 9. You will take it all the way and express it as 3i. Let's take a look at this one, the square root of, negative 300. Okay, let's simplify this, this radical. Well, many of you will probably start and just say, well, this is the same thing as square root of negative 1 times square root of 300, and that's perfectly fine. This is kind of showing every single step route. And you know that root negative 1 is just I times the root of 300. And now the I is just going to sit here and wait for me to finish this job here. This is just root 100 times root 3, and this becomes 10 root 3. And the root 3 is done, and this is just I times 10 root 3. You will generally see this written this way. 10i root 3. That's kind of the more traditional way of seeing it. The reason why, everyone, is because many people, when they write it like this, even though technically, if you look at this, this is kind of like in the bi form. The reason why we swing the I up front is because it's really easy to be careless and extend this square root too far. So that's why we keep the I right in between. So it's 10i root 3. Does that make sense, everyone? Okay, and finally, if you have something like the square root of negative 7, the 7 part, there's nothing else you can do with that, right? But from now on, you don't want to leave this. I don't want to see you leaving this as the square root of negative 7. I'd like you to see this rewriting this as I root 7, because you now have the language to deal with negative radicands under a square root. Okay? All right. Let's see. So let's go to now something like this, okay? For the most part, you are really well equipped and well practiced with simplifying fairly simple expressions involving complex numbers. And now I want to just introduce you to a couple of more, okay? And let's see. Let's take a look at this one. 1. Let's do 2 plus root negative 5 times 1 minus the square root of negative 10. Let's do that one. And then let's simplify this one, okay? 4 all over 2 minus I, okay? This one is going to be new, so hold up on that one all the way. What I'd like you to do right now is just see if you can simplify number 1 all the way through and then replay me for the answers. Okay, here I go. So here I've got a FOIL situation, right? I have a binomial times a binomial. I'm going to start out by multiplying it. So I have first 2, okay, minus 2 root negative 10. I'll deal with cleaning the radicals in a minute. Plus 1 times root negative 5. Okay, now this is the tricky part, everyone. When you're multiplying the lasts, the L, watch all your negatives, okay? This is going to become, let's see, a positive number times a negative number. We're going to have a negative root of what? 50. Positive 50. Yes, because negative 5 times negative 10 is positive 50. All right. Now I'm going to do this. Let's see. 2 minus 2I root 10 plus I root 5. Everyone see what I did there? Okay. Minus, now root 50 is the same thing as, I may go over here to the side. Root 50 is the same thing as root 2 times root 25. So this becomes minus 5 root 2. Okay. Let me make this a little bit neater. Sorry about that. This was root 10. Okay, let's take a look. Are there any like terms? Well, there are like terms, everyone, but here's where we're going to be a little bit fluid here. 2 and the negative 5 root 2 are like terms in that they are real. So I'm going to combine them as best I can, and really combining them just means writing them like this, right? Now here, follow me here very carefully. Negative 2I root 10 and positive I root 5, those are also like terms. So I'm going to go over here and write this down. Watch, okay? Negative 2I root 10 plus I root 5. These are like terms. You can even, if you want to, just think about I here just as a variable instead of thinking of it as root negative 1. And here's the question. If I ask you, how many i's do you have? Well, you really have negative 2 root 10 plus root 5 i's. Do you understand? Okay. Now remember, like terms. Root 10 and root 5, these are not like terms. Okay. Like radical terms have to have the same radicand. Some of you may be thinking to yourself, well, couldn't I rewrite radical 10 as radical 5 times radical 2? The answer is yes, you could, but notice neither of these simplify, so that's of no help to us. So at the end of the day, everybody, look what I can do. I can write this expression right here by combining like terms, and here's what's really interesting is when you combine like terms in this sense, what you see here is not exactly a whole lot of reduction in the number of things you write necessarily, but then what you have is a complex number in the form A plus BI, right? So if you were asked for this number in the form A plus BI, you could do that. Okay, I think what I'm going to do now, since I try and keep these screencasts under 15, we'll take care of how do you simplify something like this, and frankly, what's wrong with this expression. We'll talk about this tomorrow in class, okay? I'll put your homework up on the teacher page. Goodbye.